I think it's time, so let's begin. Warm welcome to everyone who had joined this webinar. We have pretty interesting things to show in this presentation. But before that, I would like to introduce myself. Hello everyone, this is Yogesh Solani. I am Senior Research and Development Engineer here at Diabatix. And my job is to work on technical development projects. I'm also host of this webinar today. With that, let's dive into the presentation because we have a lot of ground to cover today. So in this webinar, I'm going to discuss the cooling applications in electronics devices. There are a lot of pin-fin applications, but we have recently also introduced the TPMS heatsinks. And we're going to discuss both of these applications, but the most importantly, I'm going to compare pin-fin designs with TPMS designs. So the content for this presentation is I'm going to give a short introduction for those who are new in this webinar, those who don't know about Diabatix. Then we are going to talk about concept generation in thermal engineering, challenges in heatsink design methodology. This is something that unique we have developed at Diabatix, and how we do the optimization of heatsink designs. And this will be followed by a couple of case studies. First case study is about Intel 700 heatsink CPU cooler, and second is double-sided liquid cooler power inverter. Both of these case studies will have comparison of pin-fin design versus TPMS designs. At the end, there will be Q&A session, but do not hesitate to put your questions in the chat box because our moderators are also live with this webinar, and if you have any question, they will try to answer it as soon as possible. We put them in the chat box. At the end, I'm going to give you some pointers about ColdStream, how to find us, and how to use our platform for your design optimization. With that, I would like to start this presentation talking about the vision of this of Diabatix. I would also like to highlight that all the results that you are seeing in this presentation are generated by ColdStream, and this is the only tool available in the market that can not only do design and simulations, but it can also do optimizations. If you want to have a private 101 demo, please drop us a message in the private chat box. Now, if you see the things around yourself, the things are getting smarter and smarter day by day. There are electromechanical systems which are coming into these devices, which are highly driven by Internet of Things and AI-based applications. And one of the important aspects of these devices is heat dissipation and thermal management. Our founders at Diabatix really saw this thing quite early in this period. They envisioned this, and because of which we started developing smart algorithms which can empower design engineers to design something beyond their imagination. We already have few smart algorithms and we are continuously improving upon them, but over the time we also plan to introduce new algorithms which will help you make designs beyond your imaginations. Our vision was very well received by both the giants in the simulation and modeling industry, ANSYS and Hexagon, and we made them technology partners for our vision. Now, having said that, let's try to understand the conventional design cycle and generative design cycle. I would like to take an example of, let's say, PCB cooling or PCB design procedure. If this challenge is given to an engineer to do a PCB design, how he would start it and how heatsink will be designed for the case. The initial procedure will start with functional design of the PCB. He will put chips, he will create a circuit layout, and he will put necessary components on those chips so that it will functionally behave well. The later part will come in the case of thermal management, where proper designing of heatsink is necessary in order to extract the heat out of the system so that it will function to its maximum performance. The reason we need to have heatsink is because the heat accumulation, if it is not done properly, can impact not only the behavior of the component or behavior of the electronic devices, but also it can affect the longevity of these electronic devices. And this essentially gets translated into a CAD model, that is the PCB design and heatsink design. which essentially goes to a simulation engineer for heat transfer simulations, where thermal prediction, heat dissipation is calculated or is estimated, and then the possible modifications are done on the CAD model. These iterations continuously go on in a conventional design cycle till the time a desired solution is obtained. Later, this will be assisted with the field testing and other things, but the essential or the fundamental problem with the conventional design cycle is that after all this exercise, we get a solution. It might not be an optimal solution. On the contrary, in generative design cycle, we achieve something which accounts for exploring a design space. What I mean by that thing is that we can start from the scratch. We can define certain objectives and constraints, and let's say manufacturing constraints. Based on this, a generative design will generate n number of concepts. In this case, let's say 1000 concepts. And with these 1000 concepts will be spanned over a space, a design space, which will be viable or non-viable. Now, out of these 1000 concepts, user can take best 2 or 3 different concepts, and he can take these concepts forward for the detailed design optimization. By doing this, user is really exploring the design space, and he is also comparatively estimating the best possible concepts which he can take forward for detailed design generation, and thereby leading to the truly optimal solution. And this is essentially the benefit that we get with the generative design cycle, which we also try to provide it with our software platform called as ColdStream. Now, I would just like to give a very simple example here, how ColdStream really does that. As I explained earlier, there will be n number of concepts that will be investigated. On the left hand side, you can see the same investigation being happening. Each dot here represents basically one single iteration performed for a particular design. You can also see how the performance is being improved as the number of iterations are being generated. You can see the green dots, those are basically the best possible iteration obtained or the performance obtained till that time whatever iterations are happening. And over the iterative process or the optimization process, you will also see that the best performing concept will be highlighted by the darker green dot, which essentially indicates that the concept that was generated at that iteration will be taken forward for the detailed design generation, which will lead to the optimal solution. In this case, this heatsink was the best performing heatsink generated for a given problem, which could work as an initial starting point for your detailed design generation. Now, for this presentation, detailed design generation is not really the scope of the discussion, but if you are really interested to really deep dive into detailed design generation, then I would like to point out our customer support team to whom you can reach out, or you can leave your contact and they will reach out to you to help you with your design optimization and creating an optimal solution for your design problem. Now with that, let me quickly talk about the heatsink optimization. Heatsink optimization is a critical issue in electronic application, as I mentioned earlier. And so in order to define and optimize heatsinks, there are key performance indicators like the heat dissipation, energy efficiency, the size and weight of the heatsink. This is highly useful in an industry like aerospace industry. The reliability, longevity, and all of these key performance indicators, they get translated into design parameters. So for example, what material to use for the heatsink, what is surface area, what is the packing density, what is the base thickness, what is the manufacturability, and what are the operating conditions. What if I tell you that ColdStream can account for every single aspect of the design parameter? You can really use ColdStream platform to account for all of these different design parameters, and at the end of the entire exercise, ColdStream will itself tell you what was the best combination that can use for the heatsink. And this is exactly what we do when we say that we are generating smart algorithms for design engineers. Now let me take a moment and talk about the real problem associated with heatsink optimization. As I mentioned, there are n number of variables associated with these heatsink design parameters, and those essentially turn out to be a problem when it comes to n number of shapes that we need to consider for the optimization. Now let's take an example. Let's say we want to design a heatsink, and there are three different shapes available for the optimization. Now, if you want to really design a heatsink with, let's say, pin-fin type of design, in which you are considering, let's say, circular pin design, then there are already 4 different parameters we need to consider for the optimization. In this case, radius, height, spacing x, spacing y, all 4 parameters are essential to really optimize a heatsink with circular pin designs. But if you add another shape to the optimization where you really want to compare circular pins with the, let's say, rectangular or diamond pins, then individual to these shapes you need to add additional parameters like width, length, height, spacing x, spacing y. And this is a really big problem, because as you go on adding more number of heat sinks for the optimization, it starts accumulating more number of variables, which is very difficult for optimizer to account for and do the real optimization. It can also happen that it may tweak some variable which might not be associated with the geometry itself. And that is a real problem associated with the optimization using multiple heat sinks. So how really can you figure it out? What is the optimum combination if you do not consider different shapes associated with the heatsink design and their corresponding parameters associated with those shapes? And this is where we have developed a unique algorithm which will help you optimize different combinations of heat sinks, or it can help you figure it out the best possible combination for a given loads and boundary conditions and objective targets that you have set. As I have shown you in the previous slide, with different shapes, there are already different number of variables associated with them to do the optimization for. But with the unique unit cell approach that we have developed at Diabatix, the entire problem statement can be translated into 6 or 7 different variables. In this unit cell approach, a unit cell can be defined by a set of parameters irrespective of their shape. What I mean by that thing is, a unit cell can be defined by its width and height, and the spacing of the shape with respect to that unit cell. That is the spacing in, let's say, x and y. We can also account for the height inside and the base thickness, or the selection of shape from multiple combination of parameters. And with the help of that, we can really reduce down the problem from 14 variables to very few variables. The framework that we have developed, it works in a way that if you have, let's say, 3 different shapes, 4 different shapes, it will still yield in only 6 or 7 different variables, rather than ending up with 14 or 20 different variables. And this is basically the crux behind optimization that we use with ColdStream. I hope this gives you a really good idea what we do, or how we do the optimization using multiple heatsink shapes. Now let's try to understand what different shapes that we have in ColdStream and what new that we have recently introduced. So if you have used ColdStream earlier, then you already know that you have pin-fin heatsink shapes. They can be in different form like diamonds, rectangles, circular pin shapes, or rectangular fin shapes depends. But we are very happy to introduce 6 new shapes which we already have included, but I'm going to highlight it to a certain extent, that our TPMS, or triply periodic minimal surface heatsink shapes, are also available for now the heatsink design and optimization. These 6 different TPMS shapes are gyroid, schwarz, neovious, ludenoid, split pea, and diamond. With these shapes, we can also account these for additive manufacturing process design. The reason is because the shapes are self-supporting. I hope this gives you a really good idea of what different type of capabilities now we have in ColdStream. Let me quickly talk about how we model these TPMS shapes. Now, the method that we use for modeling is basically implicit modeling. And in implicit modeling, what we basically do is we represent the boundary in the form of sign distance functions. Unlike in our traditional boundary representation systems, where boundary is represented by geometric topology like points, lines, spaces, and solids, in this case, the boundary is represented by the sign distance functions. So the boundary is basically a zero locus of this sign distance function, and whatever is inside of this geometry is represented by the negative distances. Whatever is outside is represented by positive distances. One such example of TPMS heatsink design is shown on the right hand side of this chart, of this slide. In this, you can see that there is a negative sign distance, which essentially highlights the internal part of this gyroid or this TPMS, while this red portion or the red zones here essentially indicates the part which is outside the geometry. And this is how we essentially represent our Diabatix, our TPMS structures, and we use them in ColdStream for heatsink designs. Now, this brings me to the next section of our presentation, in which I'm going to talk about the case studies. We have a couple of case studies here. The first case study is about Intel 700 heatsink designs. And in this heatsink designs, we are actually talking about CPU cooling. Now, let me very briefly talk about the case study that we did. So this is a case study in which we bought off-the-shelf Intel CPU cooler. And what you see here on this image, this copper heatsink, this is something that comes with as a by default heatsink. It has saved features which basically account for liquid-based cooling within this CPU cooler. Now there is an inlet and outlet which basically takes fluid in and tries to do liquid-based cooling for this case. We try to optimize this case by creating a separate design volume, and we applied a set of objective functions and constraints to do the optimization. By the way, if you want to know much detailed understanding about this case study, then there are a couple of webinars already conducted by my colleague Niels. You can go onto our website and you can also look at those webinars. For this case study, we used a heat source as a heat that is coming from the chips as 250 watts, and we try to minimize the overall temperature in the chip region. The coolant that was used was water glycol in 40-60 proportion, and we also put pressure loss constraint of 11 kilopascal on the optimization problem. The material that is used is copper with the given properties, but the most important aspect is that we want to maintain the channel width of 280 microns in order to achieve sufficient cooling and the cooling paths for the manufacturing purposes. With these settings, we did a number of simulations. I'd like to show you a few of the simulations that we did and the heat distribution that we achieved out of these simulations. So the first simulation that we did was with the pin designs. You can see here the pin designs that is constructed in the design domain. Then here is a fin design and here is a TPMS design. For all of these simulations at nominal operating point, the temperature ranges that we see are going from about 40 to 74 degrees C. But the most important observation in all of these things are there are varying hotspots associated with the field. What I mean by that is, in certain region there is cold spot, and adjacent to there is hot spot, and such a type of non-uniformity is really not a good sign of a good quality design coming from for these cooling applications. And we also investigated fin designs, we also investigated gyroids, but all of these designs have more or less the same problem. So we went one step ahead and we tried to really create a fully custom design that is driven by the topology optimization based on fluid and flow problems, fluid and thermal problems. And what we got was very much enlightening, in a sense that if you have a fully custom design which really accounts for the fluid flow and optimizes a solution based on the fluid flow and the thermal field generated, then the fully custom design shows higher thermal uniformity, as in highly compatible or highly friendly thermal uniformity to the CPU, which is highly beneficial for the longevity and thermal performance of the CPU. This is something interesting to see, because as I highlighted earlier, the fully custom designs can really lead to the best performing optimization solutions that you can achieve for your problems. I would like to also show you some of the cool things that we can do with our platform. One of the important things that we still feel that there is no proper solution available in the market is that if you have TPMS designs or complicated structures which can be exported in the form of STEP or STL files, there are very few platforms which can really do CFD simulations. But our platform can not only do the simulations, but it can also help you to do optimization. Optimization of heat sinks, and this is one of the important benefits why you should think about using ColdStream for heat sink optimization and thermal problems. I would like to also show you a couple of comparative graphs. We not only did this simulation, but we repeated them for different flow rates. And I have a couple of comparative charts here. On the left hand side, there's a pressure drop with pressure on y-axis and flow rate on x-axis. So here what you see is that gyroids perform not so well when it comes to pressure loss, but it also appears that gyroid structures are performing worse in case of in and fin designs. Now, if you consider the temperature here, temperature performs a little bit different in case of different flow rates. Let me quickly zoom in this particular graph so that you will understand a little bit better. For different flow rates, the behavior or the performance of gyroid varies. In the initial stages of the lower flow rates, gyroids were inefficient compared to fins, but they were efficient compared to fin designs. But as we increase the flow rate, the gyroids become efficient than fin and fin designs. If you want to know more about this demo and want to understand how we optimize the heat sinks by using custom design or using standard designs, please feel free to reach out to us. Please drop us a message in a private chat box. Our expert will reach out to you and we'll set up a one-on-one call individually to figure it out what best we can do to help you set up your problem. Thank you. Yes, so having said that, now let's quickly look at the second case study, that is double-sided liquid cooler power inverter. In this case study, we are doing optimization for high-density power electronics, in which you can see the setup on the left-hand side. There are chips which are mounted on top of these copper heat spreaders. There are about 45 number of chips which are mounted on 3 different copper spreaders. There is inlet and outlet for the liquid coolant to come in and then to go out. In this case, the same setup is also present at the bottom of this power inverter. So there are two design domains which are one is on the top and one is at the bottom. So the optimization that we were doing for metal copper, there was an inlet flow coming at 9.5 liters per minute. There was heat source in the form of chips, and we put some optimization targets on the optimization that needs to be performed. So one of the important was overall temperature minimization. but at the same time we also wanted to reduce the overall spread of the temperature. So we wanted to maintain as uniform temperature as possible. With this setup, we went ahead and did optimization. So I would like to show you a couple of pin designs. So here you can see a pin design on the left hand side. Our optimizer went through the same process and found out the best combination of pins that can be obtained for this set of combinations, or so for this heatsink, where you can see about 500 pins generated at the top of the optimization design domain and about 1000 pins design at the bottom. The same exercise also shows the different type of pin designs which are created for the same setup. But we went ahead and we also did the TPMS based optimization, where we asked our optimizer to choose from all different 6 TPMS designs and come up with the best possible combination that will reduce the heat to the maximum extent. And with that, we achieved a design which looks like this. So on top, there is a completely different TPMS, which is split P in nature, and at the bottom, there is a gyroid based TPMS heatsink. Now, one of the interesting things is that because these TPMS designs are fully self-supporting, these can be easily manufactured with additive manufacturing process. Now, having said that, let's try to understand the overall performance or the comparison between pin designs and the TPMS designs. Here is a chart that shows the comparison between both of these designs. So in case of TPMS designs, the temperature minimization was the best that we achieved in comparison to pin designs. So here we achieved 346 Kelvin versus 359 and 374 Kelvin of max temperature using the optimized heatsinks. While the temperature variance was the lowest in case of TPMS structures, which was about 28 Kelvin square in comparison to 29 and 70 Kelvin square. And as we also saw in the previous case study that pressure loss was a little bit on higher side when it came to TPMS structures. We also see the same type of observation in this case study where pressure was about 1688 Pascal compared to the similar ranges in pin designs. In fin designs, we observe a little bit lower pressure drop because the alignment of the fin that can happen along the flow. With that, let's quickly talk about the key takeaways. Using TPMS structure can be beneficial because they can have lower thermal resistance in comparison to the pins. They can promote mixing, but the most important characteristics of the TPM structures is that they offer lowest volume to surface ratio. So for a given volume, they can offer maximum surface. But this comes with a price, and the price is that because of this, you may observe higher pressure drop in your flow applications. And also this comes with the larger design complexity. That means that these things can be built only with additive manufacturing or advanced manufacturing processes. Now, as we've seen in the first case study, that our generative design, which was fully custom to the application or to the objectives and constraints, performed the best among all of the designs, irrespective of pin, fin, or TPMS designs. And that is most likely a way to go forward if you really want to achieve the best performing combination or best performing design for your design problem. Now, with that, I would like to stop here, and I would like to point it out that there are ways how you can discover our ColdStream. So the first way is you can visit our website and you can try it there, or there is an option where you can contact our customer support team or sales team. They will directly get in touch with you. You can drop an email here, or you can contact this phone number here. Once you do that thing, our sales team will, or customer support team will help you out to get you on board and try to understand how ColdStream can really help you to create highly efficient and optimized designs. You can also drop a message in private chat box and our customer support or sales team will reach out to you after this webinar. With that, I would like to take up questions and answer them as possible, as much as possible. Thank you.